Welcome to the Explainer. Today, we are putting on our detective hats. We're going to learn how to look at a pretty simple chart and spot the hidden signals, the clues that tell us a story about what's really going on inside a process.
Okay, let's just dive right in with the central mystery every data detective has to solve. You look at a chart like this, right? And you have to ask yourself, am I just looking at a bunch of random dots? Or is there a story unfolding here? Is that one point just, background noise? Or is it a real clue that something fundamental has changed?
So our mission is to learn how to tell the difference between two things. On one hand, you've got common noise. Think of this as the normal, predictable, random static you'd expect in any stable process. It's just part of the system. But then there's a special cause. Now that is a real signal. It's an unexpected, non-random event that tells you something important just happened.
It's a lot like being a radiologist. Anyone can look at an X-ray, but a trained professional, they see the subtle patterns in all those shades of gray, the ones that point to an actual diagnosis. That's what we're going to learn to do. See those same kinds of patterns, but in our data.
Okay, so before we can find any clues, we need to understand our environment, the scene of the crime, if you will. So let's break down the anatomy of a control chart.
So every control chart has a few key features. First up, you've got the center line, which is really just the average of all your data. Simple enough. Then you have an upper and a lower control limit. Now, you should think of these like guardrails for your process. They're calculated using a statistical measurement called a standard deviation, or sigma, and they're placed 3 sigma away from that average. These boundaries basically map out the entire territory where we expect all that normal, random variation to live.
All right, now, if we assume the process is stable and just humming along, all that random noise is going to follow a really predictable pattern, kind of like a bell curve. And in that pattern, about 68% of all our data points should naturally fall within just 1 sigma of the average. Now, if we widen that net out to 2 sigma, we'd expect to capture about 95% of all the data points. So far, so good. Everything's behaving exactly as we'd expect. Nothing to see here, folks.
And here it is. This is the big one. This number right here brilliantly illustrates the foundation of all our detective work. A whopping 99.7% of all normal, random variation is expected to happen inside those 3 sigma control limits. And what that means is that anything that happens outside of this range is, well, it's exceptionally rare.
So with that in mind, let's move to our first and honestly most obvious clue for spotting a special cause. This is the one that's pretty much impossible to miss. This is our smoking gun, a single data point that lands completely outside of those upper or lower control limits, because we know that 99.7% of all the points should be inside those limits. Seeing one outside is an immediate flashing red flag that something unusual is going on.
But hang on a second. Could this just be a fluke? Is it possible that the random noise, all on its own, could just happen to produce such an extreme result? Could this chart be giving us a false alarm, tricking us into thinking something special happened when it really didn't?
Well, the answer is yes, it's possible, but it is incredibly unlikely. The probability of a false alarm, a purely random point landing outside the limits just by chance, is only 0.3%. That's just 3 times out of every 1,000 data points, incredibly small odds. So here's the crucial takeaway. When the odds of being fooled by randomness are that low, the advice from the creator of these charts, Walter Shewhart, was simple. It is far more likely that you'll find a real, identifiable cause for that point than that you're being tricked by the noise. So you investigate. You treat it as a real clue.
But special causes don't always shout at you. Sometimes they whisper. And for these more subtle clues, we can't just look for a single smoking gun. No, we have to look for a suspicious pattern.
To really get the logic here, think about this tragic but really powerful analogy. Imagine a plane crashes into a skyscraper. It's a shocking, terribly rare event. But plane accidents, as improbable as they are, aren't impossible. By itself, it could just be a horrific, random accident. But now, imagine just a few minutes later, a second plane crashes into the tower right next to it. What are the odds of 2 incredibly rare, almost identical events happening back-to-back by pure chance? Well, the probability is just astronomically low. At that exact moment, you stop thinking about coincidence and you start looking for a special cause. This is the very same logic we apply to our control chart. We're looking for patterns of unlikely events that, when you take them together, are just too improbable to be random.
And this brings us to our second signal, a rule developed by a statistician named Lloyd Nelson. So we focus on that outer band between 2 and 3 sigma, we call it zone A. And the rule is simple. Just look at any 3 points in a row. If 2 of those 3 points land in that zone A, boom, that's a single. See, a single point landing there isn't that strange. But finding 2 of them so close together, that's just too unlikely to be a coincidence.
Okay, so let's tie all of this together with the core principle of being a good data detective. And it all comes down to this: matching the strength of your evidence to the size of the signal.
What's so cool about this is how the logic scales. So to detect a huge, obvious shift in your process, a signal that pushes a data point way out beyond 3 sigma, you only need one piece of evidence. That single point is enough to say, hey, something's up.
However, if you want to detect a smaller, more subtle effect, one that only pushes the process into that 2 sigma zone, one point just isn't convincing enough. It could totally be noise. For that, we need more evidence. We need that suspicious pattern of 2 points to be confident that something special is really going on.
By learning how to spot an outlier and how to recognize an unlikely pattern, you've really gone from just looking at data to actively investigating it. You've learned how to separate the noise from the signal. So the final question is, now that you know how to look, what other stories are hidden in your data just waiting for a detective like you to find them?